Hi there. Today we're talking about Nyströmformer, a Nyström-based algorithm for approximating self-attention by Yunyang Xiong, Champeng Cheng, Rudrasis Chakraborty, Mingxing Tan, Glenn Fung, Yin Li, and Vikas Singh. So this paper, yet another paper that proposes a approximation to the self-attention mechanism, to the self-attention matrix in transformer models. This time it's based on the Nyström matrix approximation. That's why the model is called Nyströmformer. And why it is not called the Nyströmer, I don't know. Like, you had the chance. So I'm officially renaming this to the Nyströmer. Okay, that's the title now. That's the model now, the Nyströmer. By the way, if you're not in any language that has this sign or this sign, it's called an Ö. So Ö, you go O, but Ö. Well, it's hard to explain. In any case, as I said, this is an approximation to the self-attention matrix. The Nyström method basically takes a subset of rows and columns, of keys and queries in this case, and approximates the full matrix by just using this subset. And we're going to look at how this works. But the promise is that you can scale transformers to much longer sequences without having the classic attention bottleneck that you'd have in transformers. And the results so far are pretty good for this model, though results in single papers. You know how I feel about those. But we'll check it out. We'll go through it. If you have comments, let me know in the comments, and don't hesitate to share the video out if you like content like this. All right, let's dive in. So there is a long discussion here about transformers and this kind of bottleneck, this quadratic memory bottleneck. And if you don't know what I'm talking about, you can go watch the video on Attention is All You Need or any of the transformer videos. The paper really starts down here with the introduction of self-attention. So here we're dealing with self-attention. There is also something like cross-attention, like when you have an encoder and a decoder and you need to pass information from the encoder to the decoder. That is not self-attention. That is called something like cross-attention, or I don't actually even know what is called. This paper deals with self-attention, though I know that Lucid Reigns and Clash Luke on Twitter had a nice conversation about how you could do this also for cross-attention. I'll link to it. Check both of these people out. Yeah. All right. So self-attention. You have your input signal. This is one attention layer, right? It's usually multi-head attention, but here we'll just have one head. So you have your attention layer, which takes an input X. So your X is usually some kind of a sequence, and you want to transform it into another sequence. So we've been here a bunch of times already, and you want to know, it's probably an equally long sequence, you want to know which information do you need to pass where. So maybe this thing needs to inform those two, and this thing needs to inform those three, and this thing just needs to inform that one, and so on. So you sort of want to transform a sequence into another sequence in the next higher layer. And yeah, you want to kind of send information around so that every sequence element knows about every other relevant sequence element. The way you do this is by attention. So what you do is you construct these query, key, and value matrices of the attention mechanism simply by linear projection. So you can see that the X here is an input to all of them. What you do next is this is the crucial operation. You multiply the queries by the keys. So essentially what you do is you express the keys are vectors, and basically every sequence element is advertising what it has to offer. So the keys are vectors, something like this. So every sequence element expresses a key. The key is an encoding of what kind of information the sequence element contains. And then every sequence element also expresses a query, and the query I usually draw up here. And that is, what kind of information would this sequence element like to gather from its surroundings, right? So, and then you do the inner product, you multiply each query by each key, and you can see already like this element here is probably going to receive information from this and from this, because the inner product is very high between the query that this expresses and the keys that these express, and so on. So you can see that you need to multiply each query by each key. That's exactly this operation over here, query times keys, and that gives you a quadratic complexity in time and memory, basically. So you have usually your query matrix, and your query matrix is number of sequence elements. So your query matrix is number of sequence elements times the number of dimensions. So you have some kind of d-dimensionality for your queries, and here n is the sequence length, right? So you have one query per sequence element. One row here is one query. And then you have the keys, and the keys, and you usually write the keys as a transposed matrix, are exactly the same. So they are number of sequence elements times some kind of dimensionality, inner dimensionality. Now I'm already drawing the dimensionality smaller than the number of sequence elements, because that's usually the case. So especially if you have multi-head attention, the dimensionality can be lower, or is often lower than the number of sequence elements n right here. And then you perform this product, and what you end up with is, as we said, this n by n matrix. So this is an n by n matrix, and one element in this matrix is going to be the product, of course, of the corresponding query and key. Now, we'll get to the rank in just a second. The second notable operation here is this softmax operation. So after you've put queries and keys together, you want to perform a softmax, and that is a row-wise softmax. It says it down here, a row-wise softmax, which means that in order to so this here is simply queries times keys. This is not the self-attention matrix yet. What you need to do is you need to put it through a softmax, and in the softmax it's the same matrix except it's normalized by row, right? So the softmax is something like, the softmax of x is something like at position I, something like e to the xi divided by sum over j e to the xj. Right, so you exponentiate every element and then you normalize by the whole row. So this is the normalization over the whole row. It's sort of like the softmax at the end of a classifier, where you just have a bunch of logits, right? At the end of a classifier, so if this is your 0 line, you have a bunch of logits. One says, this class is kind of likely, this one's not, this one's super likely, but it's just a bunch of numbers, right? Your neural network's going to give you a bunch of numbers, and then through the softmax, you transform that into a proper histogram, where, you know, this one is the highest probability, this one a bit more, and these two are just really low probabilities. So the same softmax operation goes for here, because ultimately you want to know from which point do you send information where, and that is going to be a histogram. That is going to be a distribution over, so any sequence element sees the input then as a distribution over where it should gather input from and how it should weigh it when it aggregates it. People have tried this without the softmax, and it just turns out that it doesn't work as well. I guess in the future, someone might come up with something that doesn't require normalization, but, you know, it is what it is right now. Okay, so you need to normalize this. And you can see that in order to normalize, you actually need the whole row. Okay. So you need the whole row to pass it through the softmax, and that is sort of the bottleneck. If we didn't have the softmax right here, a lot of techniques would apply, a lot of linear algebra techniques to decompose this big matrix. Because if you know a little bit about matrices, then you can immediately see that if this D here, if the dimensionality is smaller than n, then this big matrix here will have a rank that's lower than n. Like, it will have rank at most D. And that means that you can decompose it into smaller parts. You can do a lot of tricks to not have to deal with actually n by n things. However, the softmax operation requires you to consider these whole rows at a time, and you can't really decompose it because it's a nonlinear operation. And that's why so far people have struggled approximating this. Now, there are other techniques like the performer and the linformer and the longformer. Actually, the longformer is just local attention. But there are other techniques, and I've made videos about most of them. So what does this paper do? They tackle the problem again of approximating this big matrix. So here is what they suggest. They say, look, what you can do, you can consider any matrix as sort of this collection of submatrices. So this notation over here, it simply means that you want to divide your matrix into 4 sectors. Okay, so you have sector 1 here is A, and then this is B, and then for some reason this is F, and then this is C. I don't know why it's F. We'll just go with the flow right here. Okay, so you can consider any matrix like this, and the goal here isn't going to be to actually do matrices that are just evenly distributed. The goal is going to be matrices that are distributed where maybe something like this. Okay, so A is super small, B and F are kind of long, tall and wide, and C is a big block. And our goal is to leave C away, to simply store A, B, and F and calculate with A, B, and F, and then leave C. And so you can see, if we can do that, that is going to be an advantage. So the Nyström method does exactly that. It leaves away this C right here, leaves it away, and replaces it by this quantity right here. So if we have A in the top left and then F and B on the off diagonals, then we can reconstruct C, and this seems like magic. We can reconstruct C by F A inverse B. Okay, and you can see it over here how you would calculate something like this. You can immediately see that you don't need this you don't run into this everything with everything bottleneck, because this right now is simply, this is n by m, and m is the size of A, and this is m by m, and this here is m by n. So unless you actually construct the full matrix, you don't need to worry about this n by n complexity, because you can just calculate with the smaller matrices. So there are two things right here. We'll go into why this might work in a second, but there are two things. So the first thing is that I have just said that you can do all kinds of linear algebra tricks. However, in order to calculate the softmax, you need to construct the full matrix, right? That's what we said. You need to construct the n by n in order to calculate. Actually, you just need to construct the entire row, but still, you need the full thing in order to calculate the softmax. This linear algebra trick won't get us around it by itself. And they actually say this. They say, look, if we do this, and this is the first kind of try at this. If we do this, we would simply, if we want to approximate the softmax matrix, we would have to have the softmax matrix first in order to then select these submatrices from it. So we would need to calculate the full rows in order to normalize them in the softmax operation before we can do these submatrices, which would, defeat the purpose. It would defeat the purpose of the whole thing. So their plan ultimately is going to be, when it's something like this. It is, here you have your X. You construct by means of keys, queries, values. You construct your, by means of keys and queries, you construct your matrix, let's call it, you construct your matrix S by, let's call that, what do we call it? You construct, let's call it keys, queries, keys. You construct this, then you construct the softmax matrix, and then you approximate it, okay? That is the naive way, let's just say, and then the Nyström method comes in here, and you can see that you still need to calculate the full matrix before you can approximate it. So it defeats the purpose. What they're going to do is simply, they're going to say, well, can't we first approximate sort of the queries and keys? I'm just going to make it like this. Can we just approximate this somehow and then and then from that calculate the softmax approximation? And the Nyström method would actually come in somewhere here. That's where I'm not really convinced, because what they ultimately end up doing is they simply end up doing the approximation inside the softmax, then applying the softmax to each of the approximation, and then calculate with these approximation. Like this, it's not really valid. It's like saying, here are two operators that you really can't interchange. Like you first need to construct this n by n matrix, and only then can you apply the softmax. And they're just saying, well, we're going to exchange the operators anyway. Yeah, so that's where the approximation is. You exchange the operation of the softmax and of the subsampling that is necessary for the Nyström approximation, this selecting rows and columns. And they do have some proofs that this converges to the true softmax matrix, but just be aware that this is where the approximation actually happens, in the exchange of operations. So this is the first thing. The second thing is, why does this even work? Why does the softmax, this Nyström approximation even work? And here is an intuition. Okay, so intuition number one, we've already said this is low rank. This is a low rank matrix. And what does it mean to be low rank? It means that the entries in the matrix are not necessarily independent from each other. So they don't carry n by n bits, let's say, of information right here, or n by n floats. Even though the matrix is n by n large, you can actually describe it with less information. That's what it means to be low rank. And so it is conceivable, right, that we can just leave away some entries of the matrix and recover them from the rest, because we already know that we don't need the full numbers, the full n by n numbers to describe this matrix. So if we somehow had a handle on the exact information we needed to describe it, we could leave away big chunks. Now, we might not have that. So, okay, so what does the Nyström method do in this particular case? Now, let's leave away this softmax problem for just a second and focus on what it does. As we said, we had our queries and our keys as these kind of tall and long matrices, right? So the rows here are queries and the columns here are keys, and we're about to do this outer product. Now we don't We don't want to do this outer product. But if we did, we would get, again, this n by n matrix. Now, the Nyström method here selects 3 matrices out of this. So first of all, what it does is it determines the so-called landmarks. And the landmarks are a subset of queries and a subset of keys that are special. They're called landmarks. Now, actually, in this paper, they calculate the landmarks by averaging over queries and keys, but for easiness, we'll simply say we'll select a subset. So right now, we're going to select, actually, let's just select 1 query and 1 key as a landmark. Okay, so these are special in some way, right? We'll see how they're special in a second. So what we're going to do is we're going to construct, first of all, we're going to construct 2 matrices right here. We're going to construct the query tilde times the keys, and we're going to construct the queries times the key tilde. Now, the tilde, these are just the landmarks, okay? So here you see that we're going to calculate our attention matrices, but instead of calculating the full attention between all queries and all keys, we'll simply calculate the landmark query attention into all the keys, right? These are all. And we're going to calculate the attention of the landmark keys into all the queries. Okay, so we've now drastically reduced, because instead of having, you know, all of the queries and all keys, we'll simply have all keys with 1 query and 1 key with all queries. So what does this give us? What can we accurately represent with these things? Well, if we have 1 query with all the keys, right, we can accurately represent this first row of the matrix right here. Because that's a wiggly line. I hope you can see that, because you simply take the landmark query and you calculate its attention, or its product, its inner product, with all of the keys, which is exactly this first matrix right here. We can also faithfully represent the first column. We can represent the first column accurately by, well, I am terrible today. Because we have the first key and all the queries, its inner product with all the queries. What we cannot accurately represent is we cannot accurately represent any entry down here in this big C matrix that we not choose to leave away. If we only calculate these 2 matrices, we don't have any entries here. Okay, nada, no. So what do we do if we actually want to know what an entry here is? Well, let's look what an entry here represents. The entry here is the interaction between query, let's say that's query 5 and key 4. Okay, the key number 4 and query number 5, we wonder, how do they relate to each other? What's their inner product? Kind of how much are they attracted to each other? Whatever you want to call it. And we don't know, but what we can do is we can ask, so query 5 and key 4, what's their inner product? And we can say, well, we don't know. What we do know, however, is how does query 5 interact with key number 1? Okay, so key number 1 and query number 1 are the keys and queries that we actually do have. And we do have the entry, like this entry right here for query 5 and key number 1. We have, check, we can calculate this. And we can also calculate another thing, namely, so this we can calculate here, and we can calculate how does key number 4 interact with query number 1. Okay, we can also calculate that. So how does query number 1 interact with key number 4? Check, we can do that. And now what we simply need to do is we need to know how does key 1 and query 1 interact. You see, we have made kind of a trip. So instead of saying how does query 5 interact with key 4, we've asked how does query 5 interact with key 1. Then we need to know how does key 1 interact with query 1, and from that, how does query 1 interact with key 4, and via kind of a way around here, we have determined the interaction between query 5 and key 4, at least in approximate. So I hope you can see that instead of going directly from here to here, as we wanted, like we wonder how much, you know, weight, here is a box. This is a box. I want to lift it onto this shelf. And I wonder how much force do I need to lift it onto this shelf. Now, what I can do this, or I can ask, well, here are a bunch of other shelves. How much force do I need to lift it onto this, and then onto this, and then onto this? Now, it's not going to be exactly the same because, you know, every single time I need to put it down and pick it up again, so there is a bit of inaccuracy, but I'm going to get a pretty good idea, and that's the approximation. So instead of query 5 key 4, we're going to do query 5 key 1, query 1 key 4, and now since this is multiplicative, you can already see that here technically, you know, I would have this twice, sort of, because you can see the two columns, the column and the row, are overlapping in the top left corner. So what I actually need to do is I need to divide by the interaction query 1 and key 1. Okay, this is a 1. And now I have the correct approximation. Well, is there even such a thing as a correct approximation? That's a philosophical question. In any case, that's how the Nyström method works. So instead of calculating the entries directly, it goes this 3-step way. It says, well, I don't have the entry, so let me check what the query I'm interested in does with the landmark keys, and then I check, well, how do the landmark keys interact with the landmark queries? And then I check how do the landmark queries interact with the key that I'm interested in. And from that, I should be able to determine about how does the query I'm interested in interact with the key I'm interested in. And that now is the Nyström approximation. So the third matrix we actually need right here is we are going to need the queries times the keys of the landmark, and we're going to invert that. So it's either a pure inverse or actually what they do here, a pseudo inverse, just in case it is not invertible in itself. So with these three matrices, we can sort of reconstruct the whole matrix under the assumption that this is low rank, right? Which it often is. Okay, you can see that's exactly what they do. So the Nyström approximation is going to be, and this is probably too pixelish, but it's going to be the query, the interaction of all queries with the subset of keys, then the interaction just between the landmarks, and then the interaction between the landmark, the landmark queries and all the keys. Well, you get the idea. And as I said, they simply switch away the operators. So what they do is they calculate each of these inner matrices. Right here, you can see queries with landmark keys, landmark queries with keys, and landmark queries with landmark keys. And then after they calculate this, they do the softmax. And after they do the softmax, they multiply them together to get the Nyström approximation. It's not valid because you need to do the softmax after, right? Or before you even select the landmarks, one of the two. So you can choose to Nyström approximate the query times key matrix by itself, but then you need to reconstruct before you do the softmax, or you construct the full queries by keys, do the softmax, and then approximate, and then you can decompose that. But again, you need the full matrix and do the softmax. This here is sort of an in-between, and we're simply going to hope that this gives us the good matrix. Now, of course, they don't hope. They actually, in the supplementary material, they show the approximation. So here, this lemma, I just think it's so funny, because what they say is, well, the following simple result states that the Galerkin discretization of the keys in the queries with the same set of quadrature and landmark points induces the same Nyström matrix, in particular the same n by m Nyström approximation S. This result agrees with the discussion in yada yada. And the lemma is, given the input data set Q and K and the corresponding landmark point set query tilde and K tilde, using 17 is what we've discussed. So 17 is, you have the softmax here, then this is this inverse in the middle, and they have a way of doing this pseudo inverse on kind of GPU. And then this is the other, the landmark queries with the keys. The Nyström approximate self-attention converges to the true self-attention if there exist landmark points Q tilde and K tilde such that, and now check this out, such that the landmark is equal to the query, landmark query is equal to the query, and the landmark key is equal to the key for all I and j. So essentially, so they frame it as, it suggests that if the landmark points overlap sufficiently with the original data points, the approximation to self-attention will be good. Well, the lemma actually says, if you choose the original data points as your queries and as your landmarks, then the approximation will be good. And I agree, like if you choose every single query and every single key as your landmarks, your approximation will be good, because it won't be an approximation. It will actually just be the matrix you're approximating. However, in the supplementary material, which is astonishingly difficult to find, like it's on GitHub, they do show the actual magnitude of the approximation. So you can see here and here, down here, they actually do have bounds on how bad this approximation is. And it doesn't seem too bad. And yeah, so the bounds are in terms of the L infinity norm. So you can make use of the fact that the softmax never goes over 1 and things like this. Right, so there is a bit of math behind it. I just thought it was funny because, you know, at the end of the day, you do switch to operators that are kind of not so, you can't really switch them. And yeah, but it appears to work. So I have also, if the authors are watching, there is a mistake. Where is the mistake? Where you discuss, so they discuss how they do the pseudo inverse. Yeah, right here. Say their algorithm converges to the inverse, to this inverse. This is the query tilde key tilde. Yep. And I think here where we say let AS be approximated by Z star, there should be an inverse right here. Probably. All right. So I hope you got how they do this approximation. All right. So they select the landmark queries and the landmark keys. They then softmax the products between landmarks and non-landmarks like this. So all of these three matrices are much smaller than the original matrix. They softmax those individually, and then they calculate them together in order to recover the full attention matrix. Of course, they never do this explicitly, because now if you have three separate matrices and it's just a linear operation like this thing right here, then you can actually you can work with them individually. You never have to go up into the full n by n dimensions, and they do show this explicitly down here. So you can see that you have this kind of convoluted path, but ultimately you have your input x, you construct queries, keys, and values, then you select the landmark points, and they select, as I said, the landmark points by segment means. So they actually average out landmark points. They average out queries and keys to get the landmarks, which I think is smarter than just selecting a subset. I don't know actually, but it seems okay. Then they calculate this inner matrix that they need to invert right here. This is m by m. They also calculate these two long and tall matrices. Then they calculate this thing right here, which is n by m. Now, if they were to calculate it together with this, it would give them back an n by n. They don't do it, however. They first calculate the product together with the values, which is ultimately what you want, in order to reduce this dimensionality n right here. And then once they calculate that, they go into, they only have an n by d matrix. They also add a skip connection down here to apparently stabilize training or make it faster. They do say it works without. This reminds me of the lambda layers, or lambda, I don't know what it was called, but is a similar reasoning. You never go to n by n, because if all of this are linear algebra operations, it is valid at this point to kind of switch the order and do things such that you never have to go up to the full matrix, right? So here is where they calculate the means. So you can see that the landmarks are constructed by averaging out a bunch of queries and keys. And a last thing I wanted to mention about this is maybe an intuition of why switching the softmax and the order of operation here, the thing I said is not valid, why this might actually be valid. So assume, why do you need the full matrix for the softmax? Because we said you have this row here, and you need to normalize over the whole row. It's valid, right? Because ultimately you want the distribution to come out. So you need to normalize over everything in the distribution. Otherwise, it won't be a valid distribution. Now, you can see that this is pretty easy for one of these two, right? If we have this thing right here, if we have the queries, the landmark queries and all the keys, that will give us a matrix like this. Okay, so this is a different matrix now than the key matrix. This is simply the landmark queries, and I think I've drawn this. If we just have one landmark, let's actually have more than one landmark, because I want to make my point. So here is landmark query 1, landmark query 2, and landmark query 3. Right? These are the subset of queries we selected, or they are the averages of queries, right? However you want to do it. And here is key 1, key 2, and so on with all the keys. Now we calculate this. Do we have a problem here with the softmax? No, we don't, because the softmax goes over the row. And in this matrix, at least, we can, we have the whole row. So we can normalize across the row. Not a problem. This gives us a valid distribution for these particular queries. Okay. Where we do get a problem is when we have this matrix. This matrix is the tall matrix, and the tall matrix is all the queries with the landmark keys. So here's query 1, query 2, and so on. And here is landmark key 1, landmark key 2, and landmark key 3. Now we have a problem, because if we want to normalize by row, we're missing a whole bunch of keys. Now, why could this still work? Now, it could still work because, as we said, these things here, they're actually the means of all the keys. So This is the mean of the first third of the keys. This is the mean of the second third of all the keys, and so on. So that might be one reason, but another reason comes from word embeddings. So if you know word embeddings, then you know that if I want to train word embeddings, what I do is I say like a cat sat on the mat. And if I want to train word embeddings in one particular word2vec, what I do is I take a particular word, like this word here, sat, the word sat, and I try to predict the surrounding words, okay? So I try to predict the word cat from sat. Now, in order to predict this correctly, I need to know how often cat appears around sat as compared to every other word in the vocabulary. So I need to know the connection, like the count. Let's say C is the count function. I need to know how often does sat and cat appear together in this context, in context, and I need to divide it by everything else that the word sat could, here X, by everything else that the word sat could appear with, right? By every other possible context. Now that is not possible usually, so what we do is we do a thing called negative sampling, and in negative sampling we simply say something like I'm just going to get a bunch of other contexts that I randomly sample from the data set, and I'm going to normalize this by these randomly sampled data points. So I'm going to replace the whole of the denominator by a randomly sampled subset, and that's going to be good enough. And this is a lot of what contrastive methods do as well. So if I want to, let's say, classify, we've seen this a lot, yeah, with these contrastive methods. If I want to classify a data point X into, wherever it needs to go, what I can do instead is I can simply say, well, I have a data point Y right here, and I know X and Y are somehow related to each other, so I want to make them close together. And I'm going to simply sample a bunch of other data points, Z1, Z2, Z3, Z4, and I'm going to make those repel each other. And that's going to be my objective. So instead of comparing with the whole data set, I'm simply going to subsample a set of negative samples randomly, and that's going to be my normalization in the denominator. Maybe something like this is happening right here, right? By subsampling a set of queries and then simply normalizing over those, you do have actually an approximation of the whole distribution. So maybe it's not that bad what they do right here. Okay, so those are my thoughts on the Nyström approximation. They do a bunch of experiments, like they here compare matrices, how they look. They do a complexity analysis, and naturally what you'll have is, instead of having the n squared complexity, you basically go down to an O of n complexity. You do have this m quantity quite a bit in here, but since m is way smaller than n, because you usually select just a small subset of landmarks, you get away with just calling it O of n. They show how this relates to other transformers, especially the linformer and the longformer, in terms of memory consumption. So here you can see as you scale up, so in 512 sequence length, the original transformer has 54 megabytes, and the Nyströmer has 35 in this case. If you select, I think the 64 is, you select 64 landmarks out of the 512. So it's not a big saving, but as you go up here, you see you can go up to a sequence length of 8,000, where the original transformer will take 10 gigabytes of memory, whereas the Nyströmer only takes 300 megabytes. So the scaling here is very smooth, it's quite linear, as you can see, and also the time required to calculate it gives you a big speed up. And it's about the same order, I would say, here as maybe the Nyströmformer, because the Nyströmformer also, it compresses down the sequence length through projection, if I remember correctly. However, they do compare to these other models in terms of, and this I think is an interesting result, and this is not in the paper yet, it just was tweeted by one of the authors. This is the result in the long range arena. So this is sequence tasks where they're constructed such that long range dependencies in the text that you analyze are of importance. And you can see right here that the standard transformer does, okay, but it has this big memory complexity, and the Nyströmer is able to match that performance. Now, we don't know yet if the Nyströmer here has, what kind of settings it has, how much memory is really saved, but I assume that quite a bit of memory is saved, and it still retains that capability of doing these long-range dependencies, as you can see right here. The other models that reduce the complexity of the attention matrix, such as the Performer, which uses random Fourier features, the Nyströmformer, which projects down the sequence length, and the Reformer, which, if I remember correctly, uses locality sensitive hashing and isn't, so that's n log n and not O of n. They all perform not as well. As always, take experiments with a grain of salt right here. We don't know yet. Also, this axis isn't, it's not centered at 0, so it looks more dramatic than it really is. However, these are promising results. And also check out the appendix if you want to know a bit more about the math, because, so in my opinion, these kind of bounds right here, they should be in the paper, because right now the paper just says, if you use all the queries and keys as landmarks, then you're good. But, what does that give you? And yeah, I fully expect this graphic here also to be part of the paper, because I think that's the most important result of the paper. Yeah, there is more to the paper, but I don't want to drag this video on forever. Thanks for listening. If you have any sort of comments, if it was not understandable, I realize we've skipped over a bunch of things and I rambled a bit, just let me know. And other than that, there is a link to the code right here. The code is super simple. It's just, what they describe in the algorithm. There is a link to the supplement. I'll leave this all in the description, and I'll see you next time. Bye-bye.